The next segment is the optimization process. And this is like the core of network training. So let's try to understand like how this optimization is done. So we use gradient descent, and you might have studied this algorithm in the past in some of the courses, maybe in statistics or so. But I will give you like a quick recap of how this gradient descent works. So, and again, I mean, there are a lot of other optimization algorithms you might have, maybe in numerical calculus, or you might have studied. But gradient descent is one of those which I think is very useful in network training. And it's a way to minimize the cost function. In our case, this is the cost function which you want to minimize. And these are the parameters which you can change to minimize this loss value. All right, so let's try to understand how this gradient descent works. And again, we'll just go with like a very simple example, a one-dimensional, one variable. But again, that can be easily generalized to high-dimensional space. So let's assume we have a function f, which operates on value x. All right. In this case, let's say x is like just one value, which can be represented by this x-axis. And y-axis is the response of that function. Right? So for each value of x, you will get some kind of response. Okay, so if you think about this, f in this case is the network, and x is like the parameters you have. Okay, so when we try to optimize this, when we try to optimize like this function, then we want like the minimum value of this function f. Okay. Oh, sorry. So f not the network; it's the loss function which you're trying to optimize, right? Sorry about that. So this is the loss function f, and we want to minimize the value of the loss. In this case, we can see that the minimum value is at this location, right? The bell location, and it can't go like any further down. That's the minimum we can achieve. So the optimization, what it will do is it will tell you, okay, for x at this position, you will get the minimum value. So when we perform the optimization, we are trying to estimate the value of x. So if you map this analogy, if you map this with like the network training, and f is a loss function and x is like your weights, in that case, you will have similar kind of curve, right? For different parameters, you will get different values. It will be a function. And what we want is, we want to find the parameters of the network. So we want such a parameters where the value is minimum. Okay. So how we can do that? So as I said, we randomly initialize the network weights. In this case, let's say x is our weights. We randomly initialize, let's say we get at A1. All right. And that will give you a loss value of something like at this point. Now we know that this is the loss. By looking at this curve, I can say that I want to go towards this direction. Right. Then I will be able to move this parameter towards the right. So what we do is we just find derivative at this location. And you know that derivative just gives you the slope of the curve. So if you compute the derivative, it will be something like this. And in this case, you can see that the slope is actually in the opposite direction, right? So it will have a negative value. Okay. So you can see here that it's 1D function, we can call it a derivative. But if it's like multinomial function, we'll have to compute like a Jacobian, or you can say like higher order derivative, right? So we'll have to compute partial order derivative for like different dimensions. But don't worry about that right now. Let's just assume that it's a one-dimensional function. We can find the derivative, which represents a slope. In high dimensional as well, it's like kind of slope of the curve. So if we have the slope, then we know like the direction, right? It's negative. Then what we can do is we can actually follow the direction of the slope. Okay. So if we follow that, then we can move like one step ahead. So this is like the increment we want to take. Now look carefully. First of all, this is again like some kind of hyperparameter, so don't worry about this. So we want to go from A1 to A2. A1 is the original location, and we compute the derivative of the function, right? And this gamma over here, it's again a parameter, and it's called learning rate. And learning rate, again, it's a hyperparameter. When you train your network, you will You will work on that a lot. So let's try to understand what that learning rate is. So that learning rate is just like how big your steps should be. Okay, so if you focus on this part, which is like a derivative of this function, so as I said, this is going to be a negative value because the slope is negative, right? So if it's negative, there is a minus sign over here, which makes it positive, and gamma is like a parameter, it will always be positive. Then what you're doing is you're actually adding this amount of value to A1, right? Because negative will cancel negative. So if you add something to A1, in which direction you will go? You will go in the right direction, right? Towards right, because you're adding something to A1. And how much you're adding? That is controlled by two things: the gradient, what is the slope over here, and the second is this gamma parameter, the learning rate. So these two control like how fast you move towards the right, or how big your step will be. Okay, so if you can compute the derivative, you can actually move in this direction. And once you are at A2, you can again repeat the process. Compute the derivative, and again, it's like a negative slope, but this time like the value of the slope is actually reducing, right? Because earlier it was like more slant, then it's going down. So then again, you're using the same learning rate, you will move to A3, and you can keep doing that. And what will happen, you can see like as you're going close to this point, your slope is actually getting lower and lower, or the derivative is going like lower and lower. And at this point, when you try to compute the derivative, it's completely going to be a horizontal line, which means the derivative is 0. So if your derivative is 0, then the second term is going to be 0, which means your value will not change. Therefore, when you reach a point when your value is actually not changing, it means you are kind of in the target location. In this case, it's the minima here. And that's what we want. So we wanted to find this value, right? A star. And that's how gradient descent help you like find this value. And again, this is one dimensional, but you can easily generalize this to high dimensional space as well. So that's exactly how your network training works when you try to use a gradient descent. But things are not that simple. Okay, so I will cover like some of those aspects why it's not simple. But as I said, like gradient descent, it's used for like optimization of functions. Now, if it's a convex function, okay, convex function is something which will have only one minima. Okay, so this is a convex function. Then you can use gradient descent and you will definitely find that minima. But your loss function will never be a convex function, right? It's going to be a very complicated function. It's always be non-convex, something like this, which means that you won't have like just one minima, you will have a lot of minimas. And then the goal is when you optimize your network, you're just trying to find local minima. Okay, if you're in this neighborhood, you are interested in this. If you are in this neighborhood, you are interested in this. And again, there could be like a lot of other local minimas. And that's one of the issues like when you train your network. And that's the reason when you train your network at multiple times, you will get different results. The reason is you are initializing your weights randomly, right? So it could be like when you initialize your weights, you start from this location. In that case, you will end up at this location. But another time you might be initializing with this point. In that case, you might end up at this location. Okay, so this will give you like two different networks when you try to optimize it.